simple trouble. So what I'd like to do is look at the forward probability at the beginning and end of the computation, and also the backwards probability at the beginning and end of the calculation. So again, it's sort of up to you whether you want to do this as an actual in-class problem or you just simply want me to sort of step you through it here. But the basic idea would be, okay, so that's the basic form of the forward probability. But okay, what do we do at time t equals 1? Similarly, from the forward probability, ideally we'd like to get the total probability of the observations summed over all possible paths. But again, okay, how do we do that? Do you want to do this as a in-class problem, or? Okay, well, I don't see any particular enthusiasm for that, so I'll just walk through it. Okay, so all right, so what we're trying to get then is this p theta 1 comma x1, I guess is what we wrote it like that, which you could think of as kind of like the initial time step of the forward probability. So intuitively, what would you do? I mean, whenever you look at something like this, the only potentially mysterious aspect of this is the fact that, just being mindless here and continuing to write vector notation on something that only has one observation in it. So, but, even if there was a real vector here, one place to start is just to start unpacking it. It's like, okay, well, what's in the package? What is this the joint probability of? Well, clearly, it's the joint probability of theta 1 and x1. So do we know how to compute that? All right. So what would you write as a computation to get that? Okay, so we've got an emission. Okay. Other ingredients? Okay, so then a prior. Yeah, I mean, this is really just the thing we looked at the very first day of class, so the definition of a joint probability being broken down into a conditional probability and an unconditional probability. So there's your prior, and there's your, I guess you'd say, likelihood, and there's your joint probability. That's pretty much that. What about then this? Do we see a connection to the forward probability in this? Well, just to start concretely, what would the forward probability, the probability expression be at time t equals n? So, the forward probability, it's just got, observations plus one hidden variable, right? So it's just the joint probability of the one hidden variable that we're interested in, and then our observations. So that we've been writing simply as this, right? And I'll write the comma like that, right? That's what we've been writing as the forward probability. So what's the relation between the forward probability here and the probability of the observations? Absolutely. So it's just our Bayesian summation to get rid of an unwanted variable in our joint probability to get what we want. So concretely, going back to our occasionally dishonest casino problem, that would be like, we're going to get at this last time step n, we're going to get some forward probabilities in each of those cells, right? We're going to add those two numbers, and that's the probability of our observation sequence summed over all possible paths through this matrix, okay? So that is basically that for this forward probability boundary case. Same thing in neater form.